so not okay. I know you won't. You have integrity. I swore I saw you with Andy.
I'm right earbuds.
Wow.
Just so you ignore me.
This is our senior class president speaking. Alright. I'm gonna start calling you Miss Trump. Get on your Twitter and rant about your feelings.
Oh, I do that in like a
You do that in a journal?
journal. I don't do them both.
Mr. Kramer.
That's probably a good decision though.
I just retweet stuff
Like-
like tweeting.
Yeah.
Alright, today we're going to do electron configuration, orbital rotation, double gas configuration, and I'll give you a few exceptions. How
All
about that?
exceptions. I was like, yes, I love those things.
Do you guys remember?
Can you like join our group? Do you think he'll have like all new houses?
I have 2 houses. We'll probably get done with it before noon.
Whoa. What are we doing after that?
Oh, party!
Okay, we're
No, we'll probably do it on somebody else.
Yeah, every year we sleep at I hope we're good.
Although I make sure our houses are done really good. So if there's like a leaf there, you know, pick it up with your teeth.
There's like one leaf left on it. Remember one year,
I don't
so
know.
big leaves.
Wow,
They just blow it. They just blow it into their neighbor's yard. I was
Well,
like,
yeah,
wait,
we-
their yard's bad.
What we do is we just, I mow it, and so it sprays in the
Last
spot in
year-
the middle,
last year we
and then I
raked
keep
the
a leaf
person
vacuum
next to
and
their
vacuum up
house.
that
Yeah.
mess, and then I'm done.
No,
Like something like a bag. I don't have
What?
that. Just mow it. And it's
2
like,
years
it
ago
mulches
because
it.
and mulches
It's
the
it.
better
wind
for
was
the
so
grass.
low on the
Yeah,
side.
Well, no, it's
Back into our yard.
What's really bad for the grass is what, if you mow it with leaves and then it rains and it snows, then it traps.
Bad.
You can't get CO2 through the snow if you, like,
Yeah, so-
paper mache's it with leaves.
Miss Peterson was actually like one of my favorite years though. She brought so much food.
Miss
And I had
Peterson
orange.
brought
Oh yeah, she does.
Yeah.
She has band
Like
parties
at first
every
I was
year.
like, nah, this is not gonna be good, but it was.
Well, all of my places give us food, so the first place we go, they give us like pop and cookies.
Well, I'm with a new group this year, so I don't know.
One year we
Well, yeah,
touch it, next year
it's
we
good
don't.
when like they just put it in the cooler outside, and they don't have to go in and associate.
Come on! You guys, if you guys just text him and tweet him, you'd be fine?
Yeah.
Oh, yeah.
Hashtag Snapchat
Old
him.
people-
Come on, you know that's
Old
true.
people are the best though.
Right.
Don't act like you enjoy it.
That's not an enjoyable thing, but it's not about what's enjoyable.
I don't like
Okay, you guys remember this? You might want to get to practice again doing this.
Yeah.
What is this? What is this for?
thing. It's the order the electrons go into things.
It's what?
It's the order of how it works.
Okay. Wow. So descriptive.
Oh
Yeah,
yeah,
that's like
so helpful.
like the order of electrons thing.
The order of how electrons fill based on energy.
It's the first thing
I remember when I did this in the
Now, you never said anything about energy.
I did. I said that's how the electrons fill it up.
Fill what up?
You did not say
A
that.
cup of water?
No, I wasn't quite sure.
Oh, I did
I
it.
did say fill.
Okay, so the diagonal rule tells us the order at which electrons fill based upon lowest energy gets filled first, then it continues to go up into higher energy. And that's what the Aufbau principle is. Okay? And Hund's rule is really representing the magnetic spins that we talked about, the ms, the plus 1/2, the minus 1/2. Do you remember that you fill each orbital with one electron before you go back and fill it with a second? Do you remember that?
Yeah. Don't know, but yes.
Okay? Now we're going to get into this. Here. Alright. You know what this is pretty clearly at this point, I hope. If you don't know what this is, leave my class and I'll never come back. But I assume you know what a valence electron is. Okay? Core electrons you probably have never heard of, but it's kind of obvious what they are. Yeah, they're just all of the electrons that are not the valence electrons. Okay? It's always more difficult to remove a core electron than it is a valence electron. Why? It's closer to the nucleus. Okay? That's going to be always the case. We'll talk about some things later on about how the first ionization energy, or the energy needed to remove a core electron, is always greater than that of a valence electron because of location. Okay, this is just a vocab word that we didn't talk much about in regular chemistry and really won't talk much more about in this class either. It just represents the groups that kind of obey the octet rule for the majority of the time. Is your S block and your P block. If you add those two electron groups up, you get a total of 8. Okay? I'm pretty sure P always comes after. That's not true. I lied. I won't say that. Right? Let's do something. Let's do electron configuration, noble gas notation for all of those. And then we're going to do some exceptions. I think I have a place. Do I have a place for exceptions? No, I don't. We'll talk about that here in a second. Let's start with, I'm just going to do sulfur, just to quickly review. And remember, what are we doing here? What exactly are we showing when we're doing this? Like when I'm doing the electron configuration of sulfur, what am I doing? What are they showing? What's the purpose? We're just, doing fancy S's and P's and putting numbers wherever we want. We don't really know what that represents. What does it represent?
The way it bonds.
Nothing to do with bonding.
The number of electrons.
Well, couldn't we just look up there and figure out how many electrons it has?
For a valence electron, maybe?
No? Can't we just look up there and figure that out?
Yeah. So I don't know. You're asking Garson.
I'm asking, what does this tell us?
How many are in
It tells us where every electron is located. Where each electron in a particular atom is located. If I'm talking about potassium, where are all 19 electrons located? What energy level? What sublevel? What orbital? Where are they located? Based on the energy of each of these. Okay, that's what this is about. It's not just, hey, let's throw some random numbers up here and make it look fancy. Okay? Okay, let's start with sulfur. Now, I don't think you'll find that these are overly challenging, but you need to be responsible for knowing which is which. So electron configuration is the one we're going to do first. Let's do it of sulfur. Very first thing you should always identify when doing configurations of these electrons is what?
How many?
How many what?
For the red number.
Okay.
Atomic number.
Atomic number. What does atomic number tell us? Are we past that low level stuff?
Proton.
Okay. Then why do we use that to determine?
Which lab has the same amount of
All
electrons.
right. Just want to make sure we haven't forgot all the easy stuff, right? So, how many electrons does sulfur have? 16?
19, I'm going to say 16.
You said 19?
On accident.
Okay.
You're talking about potassium.
Now we use this because this tells us which is the lowest energy level sublevel, and therefore which one will get filled first, and then what comes after. Okay? Now you've got to remember each sublevel and the max electrons they can have in it. So first one that gets filled is your 1s. Okay, and then we put an exponent above it that represents how many electrons are in that particular sublevel. Well, we know that an S cannot have more than how many? 2. Okay, and we gotta count for 16 electrons, so this better be full. Yeah? Okay? Then we move on and see the second energy level gets filled next, the S sublevel first. And again, same idea. S cannot have more than 2. We gotta make sure we don't do that. Okay, after 2S comes 2p. Now here we got a different sublevel. So it's going to have 6. We've accounted for 10 of my 16 electrons. Next. 3s what? 2. Next. 3p4. Now notice, we did not fill this completely, did we? Okay, so if you were to look at its outer energy level, how many valence electrons does it have? 6. Does that agree? Location on the periodic table? Okay? Now, we can always check. You have to remember a few things though here when you're checking. Okay? Our last electron's in the 3p sublevel, third energy level. Go over to the p block here. 1, 2, 3, 4. So just a quick way to check. Now, when you're in the D or the F as your ending spot, you have to remember a few things because technically the D block, energy-wise, is up a row, and the F block, energy-wise, is up 2 rows. Okay, we'll get to one of those. Okay, let's
So
do.
what adds up to 16?
What?
What adds up to 16?
That's what
2, 4, 10, 12, 16.
And
So this represents energy level, so N. This represents orbital, which, what quantum number represents that? What symbol is that? What symbol tells us the orbital? What was that? Not ML. L. Well, okay, sorry, sublevel. I should say sublevel. You're right. ML is orbitals. And this is telling us how many electrons there are in it. I don't know how to write that. Number of electrons. Okay? Orbital notation next. Probably the most tedious. Okay, this is really, the purpose of this one is to apply Hund's rule, or the magnetic, or the spins of these guys. So this is the one that represents, so we have 1s, and we represent that, the orbitals with the little, just horizontal dash. And it says 1 electron, 2 electrons. So still got our 1s. This represents how many orbitals I have, and these arrows represent the electrons. Same thing, I think we can continue to do this probably fairly quickly. I'm sure you guys are good at this point. 2p has how many orbitals though? 33. So I need 3 dashes to accommodate to get my 6 electrons. Hund's rule says I've got to put 1 in each before I go back and fill it with the other. I'm running out of space. Drawing too big. We'll go down here. And then our 3p, our 3 orbitals still here. And this is where it becomes crucial. You do not want to do this. Okay, why is that wrong? Each of them need 1 first. And guys, the reason why that is it's more stable to have 1 in each orbital first than putting a second electron in there. Even though it has opposite spins, there's still a repulsion factor to it, right? Okay? And then probably the most difficult up front, but once you figure it out, the easiest in the end is noble gas notation. Not high school noble, is it? Is it?
that's good.
What we're doing with noble gas notation is really just abbreviating. Okay, I know the noble gas notation is actually on the periodic table up there. You won't get that for a test, just saying.
What,
Right.
noble gas or what?
That whole periodic table there. I'll give you your own. Yeah, you'll use your own. Okay? So here's how we do noble gas notation. We find our desired guide. We go up in energy level and find the noble gas.
Sweaty box.
Huh?
On electron configuration, that box.
Sure. It's the non-boxed portion of what we're abbreviating.
Yeah.
Okay? So we got neon, and I like to write above my noble gas how many electrons it has so I know where I'm starting. It has 10 electrons, so I'm going to do the 11th electron all the way through the 16th electron. Now the thing here that you gotta remember, all of the noble gases, where is their last electron? What sublevel would it be in? Every single one of them. What block are they in? What block is the noble gas in? The S block?
Or B.
They're in the P block. And they're at the end of the P block, which suggests what?
That's S.
Okay, that its last electron for all of these guys will be completely filled P block. So for example, neon will end with 2p6. Argon would end with 3p6. Krypton would end with 4p6. Xenon would end with 5p6 and so forth. Does that make sense? Okay? So with that in mind, we then start after where that noble gas would end. Okay, so this noble gas, the one we're doing, ends where? 2p6. Okay? So we just filled 2p. What comes next?
Yeah.
Yes. And it will always be an S that follows because S always follows. Hello? Is this him? Hi. Yep. Okay. Can I call you back at a different time today? Can I call you? Let me see. Let's do it. Can I call you about 1 o'clock? Yeah, what is it? Nine two zero 968-8357. Okay, awesome. Thank you very much. Yeah, bye. All right. So where did I say we're starting? 3s. Okay, so now I'm going to continue to add electrons up to 16. South 3s2, 3p4. There's our 16. Notice this abbreviates that. Because if I were doing the electron configuration of neon, this is what I would have. Make sense? Okay. We have a whole bunch of time left, so what I'm going to finish up with then, actually, why don't you guys do, gosh, those are some really long ones. Where's cadmium? Why don't you guys do the electron configuration for cadmium? CD. Then I want to show you an exception. Which one's the electron? Yeah. The electron configuration.
Do we need to have a smoke?
Yeah. That one's not too. Well, I mean, just know how to write the diagonal rule, and then you just read it essentially. shell done. Violin. What was that?
I wrote down like how many electrons go into it.
Okay.
Faster.
Alright, that's fine.
So, okay. I mean, we can't use it to me. We have two types, obviously.
Yeah. Whatever you need to do. That? You get that?
Yep.
Everybody? Okay. Let me just finish with two guys, and there's more than two, but the two that I will make you guys remember, okay, that are exceptions. Chromium and copper. Okay, how many electrons does chromium have? 24. And copper is 29, is that correct? I'm just going to quickly go through what the correct, what we would expect the electron configurations to be, and then show you what they actually are. Okay? This is what we would expect them to be based on the rules that I've shared with you so far. But this is, oops, but this is not what they actually are. Okay? Now, you might want to write this down, but yeah, you probably should write this down. An atom is most stable either with a full D sublevel or a half-filled D sublevel. An atom is most stable from an electron, from an energy standpoint, having either a full D sublevel or having a half-full D sublevel. I'm just saying it would rather be full or half full versus having one like close to half full or close to full. Okay? So here's what the change or the exception is for these guys. What will actually end up happening is an electron will be taken from the S sublevel to make it half, so that D can have half. So the correct way for this is 4s1, 3d5, because that way, if you were to do orbital notation here, you would have one electron in each orbital. It's most stable from an energy standpoint to have one electron in each d sublevel than to have s filled and 4 or close to half filled in the d sublevel. And none of the YouTube stuff tell really exactly why. There was a couple online sources that I got to that explain the why, but it's really, really complicated. Okay, it just has to do with, it's, for whatever reason, the D sublevel is, if it's close to half full, it will take from S to get half full. And if it's close to being completely filled, it will take from the S to completely fill the D. It's more stable to have a full D than to have a full S. So what would this be then? Okay, those are the only two exceptions I'm going to make you know. But let's just pull out our books, and there's quite a few of them. Turn to page 316. Okay, and then what's interesting is it gets goofy later on too. So if you look at group 6, or the vertical column 6, there's chromium with the 4s1, 3d5. The one below it is exactly the same. What's interesting though is tungsten goes back. And I have no idea why. I couldn't tell you. Okay? I was trying to, search all over for the why, and there's a couple sites that were really confusing, but there's just some weird reason that these guys do this. And if you go into group 11, you can see copper and silver act the same, along with gold. I guess all of them in group 11 do that. Everybody see it? All of them in group 11 will take from the S to make D full. Okay, I think there's a few other ones too. Yeah, like in group 9, it does the same thing for, I don't even know that element name, RH45. Everybody see it? There's actually quite a bit of exceptions in here. And the why behind it is very difficult and very complicated, so I'm only going to make you know the exceptions for copper and chromium. Fair? Okay. But I'm guaranteeing you there'll be something on the test dealing with one of those two exceptions.
So is it good, like, just for my brain, like when I do it, to like write it out normal and then beneath it write out the right?
As long as you circle the one you're saying is the correct one, yeah.